Hi, everyone. It's me, Carolyn, and we are continuing our discussion on probability distributions and looking at the mean of these distribution, average of these distributions, or in a lot of times we refer to that as the expected value. If we do this experiment over and over and over again, what can we expect to happen? And here in this video, I do want to talk a few less traditional type probability is just experiments like rolling dice and things like that, and looking at them more in where we might see it being applied. So I am going to start by sharing my screen. And just kind of do us reminders. First of all, this is part 2 of section 6.1. which we are still looking at our discrete situation, and the mean of a probability distribution is often referred to as that expected value of the distribution. It kind of tells us what we can expect to happen on average. Again, it's an average if this experiment is done repeatedly. And in the last video, we found that this mean, again, our symbol for mean is mu, and we like to put an X down here to refer to the fact that this is related to our random variable. So this is just some notation. And it is a weighted mean where we add up our X values times their corresponding probabilities. We did one example in the last video with a basketball player shooting some baskets. We're going to do a few more, and then we'll also extend this a little bit to finding the standard deviation and variance, which is not something we like to do very often because it is kind of ugly and messy. You can set up tables in Excel to kind of help you do some of the grunt work, but again, it's sometimes if you're not Excel savvy, doing it by hand is just as easy as doing it in Excel. So this is one section that I really don't go to Excel or StatCrunch for that matter very often. So I'm going to just kind of do these by hand. So we're going to play a game of chance. Okay, and we have to pay $4 to play this game, and we're going to roll a die. And we're going to be paid the number of dollars that is the same that's shown on the die. And we could do this type of situation for any game of chance in the casino world, provided you can calculate the probabilities of the outcomes. And that's where the tricky part comes into play, is calculating those probabilities. So in this class, we're going to stick with some of the easier things to deal with. So like rolling a single die, drawing a single card. So for example, in this game, if you roll a 5, you will get a $5 back, but we have to remember we did pay $4 to play, so we would win $1. Okay, and we want to find out what we can expect to win or lose per game if we did this game over and over and over. I'm going to do this, kind of think about what could happen. So for example, we're rolling a single die. So our outcomes on the die are a 1, a 2, a 3, a 4, a 5, or a 6. But if we let X be the amount won or lost, because that's really what we're looking at, they take on different values. So my X's are going to be that value to this game. So the value of rolling a 1, since we're only getting $1 back, but we paid $4 to play, is actually a loss of $3. Our value of rolling a 2 is a -2. A value of rolling a 3, we'll get $3, but we paid $4 to play, so we're going to be down $1. The value of rolling a 4, well, that's the break-even point, so we basically get nothing. The value of rolling a 5, that was our $1, and the value of rolling a 6 was $2. Now, provided this is a fair a fair die, sorry, the probability of any one of those rolls is 1 out of our 6. Okay, and so now our expected value, what we can expect to win or lose per game, or the average of this game, the mean of this game, we will take our X value and multiply it by its corresponding probability, and we will add all of those up. And yes, we can do this as on a calculator. I'm going to do this longhand in fraction form just because a lot of this will cancel. It's kind of a nice problem here. Multiplying here, we'll get a negative 3/6. Yes, I could reduce plus a negative 2/6 plus a negative 1/6 plus my 0. Here we have a positive 1/6 and a positive 2/6. We have a bunch of positives and negatives that cancel. We end up with a negative 3/6. I'm going to turn that into a decimal so it makes sense in terms of money. And this gives me a negative 0.50. Okay, now your expected value could be any value that you come up with. Now our values are for X are from -3 to 2. So our expected value is going to be somewhere in the middle or somewhere in that range. It could be any number in that range, depending on what those probabilities are. So you can kind of use it as a check. This does not have to be between 0 and 1. It does not, like in our basketball problem, we had a 2-point something. So again, it had to be somewhere in the range of the values of your variable. Here our variable ranges from a -3 to 2. In the basketball problem, they ranged from 0 up until 3. So getting a value in between those makes sense. This means on average, we can expect to win or lose. In this case, we're going to lose because of the negative 50 cents per game in the long run. Okay, here's another example, how it can be kind of used in life insurances. And this is a very watered down situation, but let's just think of it this way. We got a life insurance, we got Tom or Tommy. He's going to pay $240, and I see I have a misprint here. There should be 2 M's in there or 1 M there, depending on how he spells his name. But let's say this person pays $240 per year for a $250,000 policy. And the probability that he's going to pass or die is 1 out of that huge number. And we want to know what the expected value of this policy is as it would look from the point of the insurance company. So we're going to be thinking of it not as looking at it at Tommy's point of view, but at the insurance company's point of view. And basically this year, for this particular year, now the probability is going to change from year to year as Tommy ages. But for this particular year, or for this particular situation where the probability is this number, the insurance company only has 2 outcomes. Either Tommy is going to live and everything's great, or Tommy passes on and they have to pay out this amount of money. So the value, so I'm going to just put either Tommy's going to live or Tommy doesn't. Tommy passes. Those are our 2 outcomes. Now, from the point of view of the insurance company, if Tommy lives, they got his $240. Okay. If he passes, they got his $240, but they had to pay out this large amount. So the difference, I'm doing some subtraction here, they'd be paying out a difference of $249,760. Okay. Now the probability that he passes we have is this 1 over 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. That's a probability that he is going to not make it. But the probability he lives is everything else. Remembering that the probability of a sample space has to add up to 1. So if this is he doesn't live, the probability that he does live is this number minus the 1, or 999 out of, there's 1 chance he doesn't make it, and that many chances that he does. So now to find the expected value, or what the insurance company can expect to earn or pay out for people in the same situation, because I'm sure the probability of Tommy is like maybe 60 other people in their group. So they will take that value times its probability, and then they will add those together. Excuse my drying. And again, I'm just going to use my calculator, to help me with this one. I'm not going to go to an Excel program to get the answer, because we'd have to do all the work anyway, get it to do it, and to get it to format right. Again, in Excel is not going to be all that pretty. So I'm going to take my calculator and I'm going to multiply that 240 and multiply it by my huge number there, which gives me 2, 3, 1, 2, 3, 7, 3, 4, 9, 760 over that same value. Combining those two pieces, sorry, slide this up a little bit. And dividing by this guy. I get 239.9997. So they can expect to earn, because it's a positive, on average $239 and very close to the full amount back. And that was because the amount of passing was so small. Now, again, as Tommy ages, things will change. But the thing is they realize this. And so when they create your policy costs, it's going to be based on the fact that you're going to be probably living quite a bit longer. So they're going to be recouping this value from you for many, 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 many years before they have to come out and pay that amount to you. So by the time it happens, they will have come up with way more than the amount there. So sometimes people say, well, I should just put $240 away myself. That is all fine and good, but the chance, there's always that chance that you're in a car accident, you're in a automobile, come up with some rare thing happening. And that's what we usually cover for ourselves when we're younger. We buy these policies for the just in case situations. So, but insurance companies do use these kind of values, and they do look at life expectancy value numbers, and to come up with some of these costs. So this is just a very watered down introduction to where it kind of is used. We're going to do one more example, and again, another oversimplified situation. But we've got a golf course who is going to make $800 on a fair weather day. So a nice day. But if it's raining, they only make $150. Now, fair could be anything that's not rain. Okay, so we're kind of lumping it into either it's raining or it's a fair day. Okay. And they want to find out on average, if there's a 35% chance of rain, how much can we expect to win or make? Because they're going to make money regardless, but they do make more money when it's nice out. But if it's only 35% chance of rain, on average, on those days, what can we expect to win? So again, either it's going to be fair or it's going to rain. We have no other options. The value of a fair day, that X value, is $800. The value of our rainy day is $150. The probability of those happening, well, we have a 35% chance of rain. So in terms of probability, we can think of that as being 0.35 in the rain category, because we have a 35% chance of rain. The chance that it's nice is everything else, which is 0.65. So our average, again, it's a weighted average. We will take that 800 times our 0.65, and we'll add our 150 times our 0.35. 800 times our 0.65 gives me 520. If I take 150 times my 0.35, I get 52.5. So that gives me $572.50. So on average, I will make, on these days that have 35% chance of rain, I will make $572.50, somewhere between the 150 and the 800. A little bit closer to the 800 because there's a bigger chance that it's not going to rain. Like in the previous example, our expected value was much closer to the 240 versus the negative value because the probability was so much larger on that end. Okay, I did say we could find variance and standard deviations of these pieces as well. It will be done exactly the same way as we kind of did it for grouped data. And remember back on group data. In group data, we had our X values. Those were those midpoints that we found. So in here, we do have actually X values. So I'm going to start and create my little bitty column. And the two X values I have are 800 and my 150. Okay, so just kind of going through my symbols again, we're adding up a bunch of things. This is, again, sigma squared, which means we are finding the variance. We are relating it to some distribution or some probability distribution. So X, random variable X. We're going to be adding up. If you notice, we have square brackets in the big picture. In here, we need to take our X value minus our mean, square those numbers, multiply that by the probabilities, and then we'll add those pieces up. Once we have our variance to find our standard deviation, we simply take a square root of that. Okay, the hard part was always getting that variance. And again, not an easy way to do it when it's this type of situation where technology is involved. So I'm going to be, first of all, taking my X and subtracting off my mean. And again, reminder, my mean that we just found was at 572.50. So I'm going to take my 800, subtract out 572.50. I'm going to get that value. I'm going to do the same for my here I get 740. Oops, that's not right. 800, wrong number in my calculator. Okay, 227.5. All right, and we're gonna do 150 minus that number, 572.5. That gives me a negative 422.5. So those are my pieces inside here. Now what we need to do is square those. So 227.5 squared is this really, really, really large number, 51756.25. And we are also going to square that other number, remembering a negative times a negative is a positive. Okay. In our grouped data, we would then add these pieces up and then divide by our total number of people. But here, these are weighted. So we are going to weight these by multiplying that piece times our probability. So we're going to be multiplying each of these pieces times the probabilities. I'm going to take this one times 0.65 and this one times 0.35. Because those were the probabilities of those pieces. I have this guy still in my calculator, so I'm going to do him first. 62477.1875. And 51756.25 times 0.65 is 33641.565. Can't really read that, sorry. That's a 5. And then we will add those two pieces together. And I get that my variance for this guy is 96118.75. So I added those two pieces together and came up with this. That's my variance. To get my standard deviation, we're going to take the square root of that number. And I come up with 310.03, and there's more digits, but that's pretty close. There's a 0 after. So we will round it there. And this is kind of a large standard deviation, mostly because these are kind of spread apart. They're not very grouped together, the 800 and the 150. And this guy is weighted quite a bit more heavily than this way. If we'd switched the weights around, things might have been a little different, but our expected value would have been different too. But that's just some values on how we can find that standard deviation of that distribution. We don't do this very often. And it's not, I haven't seen it used a whole lot as far as in these contexts, mostly because we don't do a ton of work, at least I haven't done a ton of work with the probability distributions of just discrete random variables. A lot of times we will use more continuous models to work with them, or we do models that are a little bit easier to handle. But we are going to continue our talk in the next section with looking at one particular discrete random variable. One that has many applications, though. So it's not something that's just one and that's it. It has lots of different situations that fall under that category. But that will be in our next section. If you're having struggles with this material, please email me so we can talk. Otherwise, I will see you in the next video.